So this lesson is going to serve as an overview of the Chapter 4 lecture. And as with most lectures, we usually start off with a new set of vocabulary words, and we have three here right at the beginning. The first is event. An event is any collection of results or outcomes from a procedure. And a simple event is an outcome or an event that cannot be further broken down into simpler components. And then we have the sample space. The sample space consists of all possible simple events. And I know that you're probably thinking that that is meaningless at this point. So let's look at some examples, and then we will use these terms as necessary. And hopefully by the end of the lesson, the definitions will make more sense to you. So example 1 says, suppose you are going to toss a coin 3 times and observe each outcome. So the procedure in this case would be 3 coin tosses. And one of the outcomes could be that you toss a head, and then a tail. And head, tail just happens to be just one out of the 8 possibilities, right? We could have all heads. We could have 2 tails. We could have 2 heads. We could have all tails. So there are 8 different possibilities. And just to get some practice with probability with sample spaces, what would be the probability, let's say, that, what would be the probability of rolling 3 tails? Well, if you look at the 3 T's inside the sample space, that is only one event, one particular event out of a possible 8. So the probability of rolling, flipping 3 tails in a row would be 1 out of 8, or 0.125. What about the probability that you would flip a coin 3 times and get 2 heads? Well, you could get 2 heads right at the beginning, or you could have a situation like this where you have a head, a tail, and a head, or you could have a tail on the first flip followed by 2 heads. So the probability of flipping 2 heads is going to be 3 out of 8, or 0.375. So the sample space is very important because it tells us the total number we are using for our probability, and that is going to be the denominator of the fraction. So in this case, the sample space consists of 8 events, and therefore we divided by 8 on those problems. Example 2. A recent poll of 1,010 adults in the United States showed that 202 of them vape. Find the probability that a randomly selected adult in the U.S. vapes. I'm going to apologize. I need to update my notes. Obviously, it used to say smoking, but I tried to make it a little more current. So let me just put a temporary note here. I'll have to erase it momentarily, but this should say, what is the probability that a randomly selected person is a vapor? Let's see. This is very awkward. I apologize for my handwriting. I usually try to do better. So that should not say smoker, but vapor. So if we did a randomized poll and found out that 202 out of 1,010 adults vape, if you were to randomly choose an adult, what's the probability that that adult vapes? Well, that's going to be 202 divided by 1,010, which is 0.2, which is 20%. So 20%, I'm sorry, 20% of adults vape. Therefore, you would have a 20% chance of randomly selecting an adult who vapes. Okay. Let me try to get rid of that little adjustment there. Okay, so looking at example 3. Example 3 says, suppose you decide to roll 2 die. Draw the entire sample space below and then answer the following questions. Okay, so if you look down at the table, let's let this top row here, this header, represent the results that could occur on one of the die, and we will let this column on the far left represent the possibilities on the second die. And what I did to save time is I went ahead and filled in this grid by simply adding the corresponding rows and columns together. So I added the 1 and the 1 and got 2, and then 1 and 2 and got 3, and so on, all the way down to the lower right box, which is simply 6 plus 6. So the reason I did that is because we're going to be looking at sums for at least a couple of these problems. So look at part A. It says, what is the probability that the sum of the dice is an even number? Well, if we look at this table, we can see that even numbers appear pretty much, or actually every other entry, right, on each row. And since there are 36 boxes that we had to fill in, and 18 of those are even numbers, then 18 out of 36 are even, which is 50%. So that takes care of part A. Part B says, what is the probability that the sum of the dice is 7? Well, you can tell that 7 occurs across this diagonal here, and that's going to be 6 out of a possible 36 outcomes. So 6 out of 36 is 1/6. So the probability of rolling a sum of 7 is about 0.1667, which means about 16.67% of the time when you're playing a game, you're going to roll a 7. What is the probability of rolling snake eyes? Well, snake eyes occurs when you roll 2 1s, right? So the probability would be the 2 1s that give you a sum of 2 here. And that's only 1 out of the 36 possible outcomes. So 1 out of 36, which is 0.0278. And part D, what is the probability of rolling doubles? Well, you roll doubles when you roll a 1 and a 1, a 2 and a 2, 3 and a 3, 4, 4, 5, 5, and 6, 6. And that's going to be 6 out of 36 as well. So that's 0.1667. So each of these particular problems, A, B, C, and D, they're concerned about different events, right? One event could be the probability that you roll an even number, or another event could be that you roll a sum of 7, or snake eyes, or the event may say, what is the probability of rolling doubles? Those would be the events. And the sample space would be all of the possible outcomes. And for this particular example, we had 36 possibilities each time. The complement of an event consists of all outcomes where A does not happen. For example, in example 2, we found that the probability of finding a person who does not vape is 20%. So the probability that a person does not vape would be 100% minus the 20%, which is 80%. So if 20% of the population vapes, then 80% of the population does not vape. In other words, we could think of it as a partitioning of the population into 2 groups. One group consists of those who vape. The other group would consist of those who do not vape. You're either in one category or the other. And since I do not vape, I would be in the 80%. What about you? Okay. A word of caution for those of you who like to YouTube and Google for extra statistics help. The complement of an event, our textbook tends to use this notation with the bar over the A, or whatever the letter happens to be. But a lot of books use different notations. The tilde is popular. The prime symbol for complement is popular. I've seen this one here. But make sure you are familiar with all different types, because you are a statistician. You're becoming more and more proficient at statistics. So make sure that you do realize that these are all the same. And I tend to use them randomly for some reason anyway. So make sure that you realize that whenever you see any of these symbols, they all mean the same thing. It just means not A, or the complement of A. And if you look at the probability of A and the probability of not A, or the complement of A, the sum is always 100%. Going back to the vaping problem, we figured out that the probability of A was 20%, and the probability of not A was 80%. And of course, 20% plus 80% is 100%. This next statement here is crucial for the rest of the semester. So keep this in mind, and I know we talked about it a little bit prior to this lesson, but an event is considered unlikely if the possibility is less than or equal to 5%. So let's look at example 5. Suppose you roll a die 3 times. Is the probability of rolling an even number all 3 times a rare event? Why or why not? And then it says, what about rolling 2 even numbers in a row? I'm going to only focus on the first question. If you toss a die 3 times, what is the probability that you would roll an even number all 3 times? So the way I have it set up is the probability of an even on the first roll and an even on the second roll and an even on the third roll would be 1/2 times 1/2 times 1/2, which is 1/2 cubed, or 0.125. That's 12.5%. And since 12.5% is larger than 5%, rolling an even number 3 times in a row is not unusual. Remember, an occurrence is unusual if it happens to have a probability that's less than or equal to 5%. And going back to the and situation here, we have E1 and E2 and E3. So whenever we use the conjunction and, that means we have to multiply the probabilities. A compound event is an event combining 2 or more simple events. And this table here is an example of a compound event because we have people who are using drugs. We have those subjects who do not use drugs. They're in the column on the left. And then if you look at the top row, we have those who test positive on a random drug screening, or I guess in this case, a pre-employment drug screening. And then we have those who test negative. So we have multiple events going on here, right? We have 2 groups. We have drug users, non-drug users, and then we have in the other group, those who tested either positive or negative. So this is an example of a compound event. Example 6 says, suppose you randomly select one of the 1,000 subjects in the table above. What is the probability of selecting a subject who had a positive test result or uses drugs? And remember, when we use the conjunction or, that means we end up adding in the probability calculation process. And the formal addition rule says that if you want to know the probability of A or B, that is going to be the probability of A plus the probability of B minus the probability of both. The reason we have to subtract out the probability of both is because some people are in both A and B, and we don't want to count those people twice. So let me see if I can shrink the size here and hopefully get all of this on one. Okay, there we go. So go back to the question. What is the probability of selecting a subject who had a positive test result or uses drugs? Well, let's take care of the first part, the probability of A, or the probability of having a positive test. Well, how many people had a positive test? Well, the positive test results are in this column here. And the probability of testing positive, well, how many tested positive? Well, we had 134 people out of 1,000 who tested positive. And then we're going to add to that the probability of B, or in this case, the probability that they use drugs. Well, how many people use drugs? If you look at this row here, we can see that we have 50 drug users. So we have 50 out of 1,000. But notice we counted the 44 twice, right? Look at the crosshairs. The reason we counted 44 twice is because we counted them already for being for testing positive, and then we counted them again, right, for being drug users. So we need to subtract out that 44 out of 1,000, which ends up giving me 14%. So the probability of selecting a subject who had a positive test or uses drugs would be 14%. So let me just kind of put that in an easy scenario. Imagine we had all of these people in one room, all 1,000. And you walked in there and you said, I'm going to randomly choose one person, and I wonder what the probability would be that they happen to use drugs and they happen to test positive. Well, you have a 14% chance of randomly choosing someone who met both conditions. Okay. I apologize for the scan. It did not pick up my Venn diagram very well, and whenever I try to draw on this program, I tend to make things worse. So please refer to your hard copy of the notes if you need a more complete diagram. The two events, A and B, are disjoint or mutually exclusive if they cannot occur at the same time. So this is actually another circle here. Notice that these two circles have an overlap, right? They overlap right here in the middle, which means that they can occur at the same time. But if you look at this picture over here, right, we have this part of the Venn diagram. That's the probability that A happens, and this is the probability that B happens. Notice they do not occur at the same time. So when they cannot occur at the same time, they are mutually exclusive. For example, you cannot flip a coin and have heads and tails show up at the same time. That's not going to happen. Those are mutually exclusive events. Is it possible to roll a die and to have an even number and the number 2 to occur? Well, that could happen, right? Those are not mutually exclusive. You could have a 2 to show up and an even number, right? Because 2 is even. So 2 and an even number occurring, those would not be disjoint or mutually exclusive. Example 7. Based on data from a recent Harris poll, the probability of randomly selecting someone who believes in the devil is 60%. If a person is randomly selected, what is the probability of selecting one who does not believe in the devil? Well, this goes back to what we said earlier about the complement. If 60% of the population believes in the devil, then that means that 1 minus 60% or 40% do not believe in the devil. So that basically means that if you were to go into a crowd and you randomly choose one person, there is a 40% chance that that person does not believe in the devil, because there's a 60% chance that the person does. Another rule that is very important in probability is the formal multiplication rule. So make sure that you are familiar not only with the formal addition rule that we just did for the drug users, but make sure you're familiar with the formal multiplication rule as well. This is the probability of A and B. Again, when we see the conjunction and, right, we know we have to multiply. And the probability of A and B occurring is the probability of A times the probability of B given A has occurred. So let's look at example 8. Airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 810 scales at JFK and LaGuardia, and 102 scales were found to be defective and ordered out of use. So they randomly selected 800, well, actually they chose all 800 scales. And they figured out that out of the 810 scales, rather, 102 were defective and taken out of use. So part A says if 2 of the 810 scales are randomly selected with replacement, find the probability that they are both defective. With replacement means that you find a bad scale, a defective scale, and let's say you label it, but for some reason you decide to put it back in the group so that you still have 810 scales, right? So the first time you randomly choose a scale, the probability that it is defective is going to be 102 out of 810, because we know that 102 out of the 810 are defective. And since you put the defective scale back in and you randomly choose again, you still have a 102 out of 810 chance of getting a defective scale the second time. So the probability of choosing a defective scale and then another defective scale with replacement is 102 out of 810 squared, which is 0.0159. But what if you are going to randomly choose 2 scales, but you are not going to put the first one back in? It almost makes sense not to put the first one back in, right? Because it's of no value anyway. But so in this case, this to me is the more realistic situation, right? You draw a scale, randomly choose a scale that's defective. You keep it out, right? And then you draw another scale. And what's the probability that the second one is defective, given that the first one is defective? So that's how you would actually read this. What is the probability of getting a defective scale on the first draw and getting a defective scale on the second draw, given you chose a defective on the first? So the first time you reach in and randomly choose a scale, there are 102 out of 810 that are defective. And since you're going to keep that defective scale out, when you reach in a second time and randomly choose a scale, there are only 101 defective scales out of 809. So why 809? Because you left the first scale out, right? And then went back and chose another scale. So that means you only had 809 in there the second time. So if you compute by multiplying, you end up getting 0.0157. I do encourage you to double check my calculations. I usually calculate very quickly on the calculator, and sometimes I do make errors. Let's go back and talk about A and B with regard to independent and dependent. On part A, since we took the first defective scale that we chose and put it back in the population, then basically the second time I drew, it was the same experiment, right? We had a 102 out of 810 chance both times. That means we have an independent process because one outcome did not really affect the other. But if you look at part B, where we kept the first defective scale out, well, when we took the first scale out and did not put it back in, it lowered our sample space, which means that it's a dependent situation, because what happens in the first draw is dependent. What happens in the second draw is dependent on what has happened in the first draw. Okay. Example 9. Suppose that 4 digits, 0 through 9, are randomly selected with replacement for a lottery ticket. Notice this is with replacement, so that's going to be independent. What is the probability that at least one of the digits is 0? Well, the probability of having at least one of the digits to be 0 is going to be 1 minus the probability that none of the digits are 0. And the probability that none of the digits are 0 is going to be 9 out of 10 to the power of 4. So where did I get the 9 from? Well, if you count 0 through 9, that's actually 10 possible digits, but we do not want 0 to be the outcome, which means we have 9 options. 9 out of 10 will not be 0, and since we are using 4 digits, that would be 9 out of 10 4 times, right? So that's 9/10 to the power of 4. So the probability that none of them, or at least one is 0, is going to be 1 minus that, which is 0.3439. I do know from my experience when I was a statistics student and from teaching this course, students really do not like the at least one situation. But the more you think about it and practice it, the easier it becomes. So don't give up on that. Continue to think about it, and it should come to you at some point. Example 10. A bucket contains 7 red marbles, 3 blue marbles, and 10 yellow marbles. If you draw 4 marbles with replacement, that means you're putting the marbles back in after you draw them out. What is the probability that they will all be yellow, all 4 of them? Well, these are independent events. Since these are independent events, then the denominators stay the same, 20. So the probability of a yellow on the first draw, and a yellow on the second, and a yellow on the third, and a yellow on the fourth, well, since 10 of the marbles are yellow, each time I have a 10 out of 20 chance of drawing a yellow, which is 0.0625. Part B, what is the probability of drawing without replacement? A red, then a blue, and then a yellow. This time I'm not putting the marble back in, which means my sample space is going down each time. So the probability of a red on the first draw, and then a blue on the second draw, given I had a red on the first, and a yellow on the third draw, given that I drew a red on the first draw and a blue on the second draw, is going to be 7 out of 20 times 3 out of 19 times 10 out of 18, which is 0.0307. So where did the 7 out of 20 come from? Well, that's the probability of drawing a red on the first draw. And since there are 7 red marbles, that's going to be 7 out of the 20. And remember, we're not replacing the marble. So we now have 19 in there in the bucket. So when I reach in, the probability of getting a blue is going to be 3 out of 19 because there are 3 blues in the bucket. And then the probability of getting a yellow on the third draw after I drew a red on the first and a blue on the second. Well, how many yellows are in there? Look at the problem. It says that 10 are yellow. So 10 out of now 18 marbles. And again, check my calculations, but I got 0.0307, which means slightly more than 3% chance that if you were to reach in that you would draw a red and then a blue and then a yellow. Part C, suppose you draw 1 marble. What is the probability that it is white? Well, we don't have any white marbles. There are 0 white marbles, so the probability would be 0 out of 20 or 0. Part D, we really do not discuss in class, and we don't test on this type of problem. It's a combination problem, but I did want to leave it in here. So my challenge to you would be this: study the question and study the solution here and see if you can make sense out of it. If you can't, I would not stress over it too much. But if you can figure it out, that would be a little extra for this lecture. Example 11. Suppose you must create a 6-digit password where the first 2 digits are alphabet, upper or lowercase, and the last 4 digits are numerals. How many different passwords are possible? Okay, so we have to have 6 digits, and the first 2 have to be upper or lowercase. And it doesn't say that we cannot reuse the letters, right? So we can use the same letters and numbers over and over again. Well, we have 26 uppercase alphabet letters, and we have 26 lowercase alphabet letters, and we have 10 numerals, right? 0 through 9 we could use. So the first time we pick a digit, it has to be alphabet, so we have 52 options. When we choose the second digit, we still have 52 options because it doesn't say that we cannot repeat the same letter. And then we have to make sure that the last 4 are numerals. And we know that we have 10 possible numerals each time. So we just multiply 52 times 52 times 10 times 10 times 10 times 10. And I received, let's see, I calculated and got 27,040,000. That means that there are 27,040,000 different passwords under this particular scenario. Example 12 is the factorial rule. A small classroom has only 6 students. The teacher wants to line them up to go to recess. How many different ways can she line them up? Well, that's going to be 6 factorial, which is 720. So she could actually line these students up 720 different ways. This formula here is for the permutation rule, and the TI-84 will do this very nicely for you. So if you missed lecture, you might want to stay back next week and ask me how to show you how to do it on the calculator. But let's look at example 13. Remember, permutations are used when the order matters. Suppose a teacher with 6 students wants to choose 2 to represent her class on student council. How many different ways can she choose a president and a vice president? So here order matters because we're choosing a president and a vice president. So if she chooses the first student to be president and the second student to be vice president, that would be totally different if she had chosen the first student to be vice president and the second to be president. And if order matters, we use the permutation rule. So the probability of 6 choose 2 is 6 factorial over 4 factorial. And I just used this formula right here. So she can actually choose, she has 30 different possible ways that she can choose 2 students for president and vice president in her class of 6 students. And finally, we have a combination rule that we use when order is not important. Suppose a teacher with 6 students wants to send 2 students to a meeting. How many groups of 2 are possible? Well, here the order doesn't really matter, right? She just wants 2 students to go down and participate in a meeting. She's not assigning a role to these students. So this is called a combination. This is a combination of 6 choose 2. And if you go through the formula here, where N is the number of students and R is the number she is choosing, then you can see that there are 15 different ways she can send 2 students to a meeting. So this concludes my overview for lecture 1. I hope this helps, and I will see you later. Thank you.